Hello, my name is Guilherme. Welcome to the presentation of our paper entitled Enhancing Deformable Local Features by Jointly Learning to Detect and Describe Keypoints. In this work, we tackle two fundamental problems, detecting and also describing local features that are robust to deformations. To our knowledge, this is the first method that tackles both detection and description of local features optimized for non-rigid surfaces. To achieve that, the proposed network is trained with a cooperative strategy that learns to detect key locations that are suitable to deformation-aware local descriptors. Deformation awareness is achieved through the non-rigid warper module, which is a spatial transformer that accommodates for local non-rigid distortions. The fusion module consumes both distinct and invariant features and outputs a new feature embedding that has both distinctive and invariant properties. DOLF achieves state-of-the-art results on standard matching metrics and also real-world applications, even though it was only trained on synthetic warps. If you take a moment to look around you, you will see an abundance of surfaces that are not rigid, that bend and flex, deform and adapt. The human body, with its articulations and wide range of motion, clothes in the wind, our body tissues and flexible materials, such as metal, plastic, and rubber, can significantly deform in short periods of time. Handling these deformations in images can be a challenging task. In this realistic simulated deforming surface, we can perfectly track a pixel and extract a centered local image patch to visualize in detail the effects of non-rigid deformations. In addition to the well-known rigid transformations such as scale and rotation, it is possible to observe local non-rigid distortions affecting the pixels together with illumination changes. The non-rigid deformations pose additional challenges for standard architectures such as convolutional neural networks in the context of local feature matching. This is one of the main reasons why almost all modern feature detectors and descriptors usually only consider affine transformations. But why do we need deformation-aware local features? Let's take a look. By empowering state-of-the-art local feature methods with increased robustness to deformations, several possibilities for real-world applications open up. For example, deformable registration, non-rigid image registration, deformable object retrieval, and deformable surface tracking. All these applications can enable solving critical tasks in medical imaging, industrial environments, and agriculture. Our proposed architecture is composed of three main components. Given an input image, an hourglass CNN backbone is employed to compute mid-level feature representations and also produce a detection heat map. The mid-level features, which have a larger receptive field and intermediate-level semantics, are used as input to the non-rigid warper module that efficiently regresses a local template splines warp for each key point. The warp is used to resample local patches from the original image. With the resampled warps, a low-level patch CNN is used to extract local features with increased robustness to deformations. Notice that at this point we have two types of complementary local features. The invariant low-level features robust to geometric transformations, and the intermediate mid-level features having rich information about texture patterns. We propose a fusion layer that consumes both features and outputs attention weights that are used to merge the two types of features. The descriptors are concatenated and weighted by the attention weights to compose the final descriptor. Our training framework is designed to make both key points and descriptors to work cooperatively to extract key points optimized for the descriptors. During training, a pair of images with ground truth flow field relating them is used. We use an image augmentation pipeline that generates synthetic image pairs that are generated on the fly during training. This approach helps us to deal with the current gap in research, where there is no specific large-scale training dataset for non-rigid image matching tasks. During training, we sample from the detection heat map distribution. The detection heat map is divided into a grid of 8 by 8 pixel cells, each containing its own local key point distribution. This strategy is similar to the one proposed in DISC and allows one to deal with the inherently discrete process of selecting key points in a differentiable manner. But in our work, the reward strategy is modified to penalize key points in unreliable regions according to the descriptor performance. even if the key points are repeatable. This allows the network to select reliable points to be matched. Finally, key points and descriptors are optimized jointly. For the detection branch, policy gradient is used to optimize the detection heat map. For the descriptor branch, the descriptor space is optimized using the hard triplet loss. Although the loss objectives are different, the heat map and descriptor optimizations interact with each other via the reward function, which depends upon description. Although DOF were only trained using synthetic deformations, we show that DOF displays significant generalization to real deformations, as we will show on the next slides. In this example, we show in detail the matches and mismatches of disk and DOF for an image pair with deformations. Even though disk was trained on Megadepth, which is a diverse collection of 3D reconstructed scenes, it struggles to produce matches in some regions where the surface is deforming. In contrast, our method produces more correct matches, especially on deforming regions. DOF is able to deliver state-of-the-art results and mean matching accuracy compared to both deformation-aware descriptors and even learned matchers such as superglue. Another interesting property of DOF is its strong invariance to rotations alongside deformation and illumination changes. After about 80 degrees of in-planar rotations, several methods completely fail, including state-of-the-art methods such as superglue and disk. DOF also displays competitive results in large-scale changes, obtaining similar performance to superpoint and superglue under extreme scale changes. Below, we show a challenging non-rigid image registration using DOF using a noisy laptop webcam. It is possible to observe challenging illumination and rotation transformations besides deformations. DOF is able to generate meaningful results even in very challenging transformations. Here, we demonstrate DOF capabilities for the test of non-rigid 3D surface registration. Under a large rotation plus deformation, superglue and disk fails to provide a meaningful alignment. In this other example, the challenge is to deal with the highly repetitive patterns besides deformations. DIO, which is a recent deformation-aware descriptor, and disk cannot handle the high ambiguity of the scene. In this other image pair, with visible deformations, all methods but ours deliver a consistent alignment between the source and target meshes. Regarding accuracy, DOF is able to provide more accurate registrations considering both 3D and 2D errors, showcasing the advantages of the deformation awareness in cooperative detection and description of key points for non-rigid matching tasks. You are welcome to visit our project page by scanning the QR code or accessing the website. Thank you for watching.